In this video, we're going to be talking a bit about isomers. So a lot of this is going to be reviewed like we've seen in quite a few of these videos before, but there will be some new things that we haven't seen before, and we're also going to start applying these to bigger compounds that are a little bit more complicated. So we'll have to see how that works out and how we can apply it to things in inorganic chemistry. So some basic definitions to start off with. Remember, isomers are just things that have the same molecular formula but tend to have different properties. And they can be broken up into a couple different families. So for example, we have the stereoisomers, we have the structural isomers. When we have stereoisomers, what we're talking about is things that have different arrangements of our constituents but have the same bond features. We'll see some examples of that here in a minute. When we're talking about structural isomers, we'll see that they have different bonds within them. Now, underneath each one of these, we get some more different categories. Under stereoisomers, we have geometric isomers, and we have optical isomers. Over on the structural, this is where we're going to see some of the new stuff, specifically the linkage and the coordination isomers. And you've probably seen constitutional isomers before, so hopefully those will be the review. Really, the two that are going to be interesting are going to be here and here in terms of inorganic chemistry. All right, when we think about geometric isomers, probably what pops up first in our head is that of cis and trans isomers. And this is when we're looking at two substituents that are on the same side for cis or on opposing side, which would be the trans case. But we can see this occurs in other types of geometries just outside of what we saw in orgo. So for example, here we have an inorganic example where we're looking at something that's in the square planar geometry. So over here, I've got two species that are on the same side. So this would be our cis isomer, whereas here they're on opposing sides of that square planar complex. So we would have a trans geometry. We can also get cis and trans forms for octahedral complexes. So in this case, here I've got two chlorines that are at 90 degrees to each other versus 180 degrees. 180 is where we'll call trans. The 90 degree in this case is where we'll call the cis. That's kind of the same side in this case. And what's really fun about this in inorganic chemistry, they can have wildly different properties. For example, when we look at this cobalt complex, if it's in the cis form, it's actually going to be a violet color, whereas if we put it into the trans configuration, it actually comes out as a green compound. That's pretty cool. We haven't seen that before, probably. So we'll talk a little bit more about that when we talk about coordination chemistry later on in the semester. A good example of a transition metal that has isomerisms that are important is that of the case of cisplatin, which was one of the first anti-cancer drugs. It's a relatively simple complex of platinum that is in a square planar configuration. So we actually have now the two ammonia that are on one side here, so that would be our cis configuration. What was fun about this is it can break through the cell, get into the inside there, undergo some hydrolysis, and then act to actually bind up DNA so that it can't be repaired, and it will start disrupting the normal function of cancerous cells. So this was one of the first drugs, but it was important on its isomer. If we were to change this to the trans isomer, we saw that it had absolutely no therapeutic effect, and actually it was quite toxic. So this was kind of a nice piece for isomers in inorganic chemistry. When we get to larger things like octahedral complexes, we'll see there's more variety that we can have for isomers. Specifically, we have facial and meridional types of isomers. And this really comes down to looking at how those substituents are put around that metal center. So for example, we think about an octahedron is where we get the name of our octahedral complex, and each face is in a little bit of a triangle. So if each point of that triangle has the same thing on it, that would be a facial isomer because now it's the face of one of the octahedrons. If we look kind of in the ChemDraw version that we have here, here we can see the plane around the equatorial sites there, and here is that face of the octahedron there. That is different from the meridional case, where now the three that we put go almost around the outside of our system here. So it's going kind of around it here, which is just like we have in geography. We have meridians that go around the globe. Same idea here. Here we're going to see that that is what we call the meridional complex, or the meridional isomer. Optical isomers is another thing that we saw in orgo quite frequently. This is when we had the mirror images that were non-superimposable. So commonly how we were taught to look at this is to draw your molecule and then draw the mirror plane here and do the reflection and say, hey, can these be rotated in such as a way that they overlap? And in the case of something like this, we'd see that no, we cannot. If we tried to rotate, for example, R2 to the same side position, so coming over here, we'd see that now we would have our R4 position. It would not be going back like we're seeing here, it would be coming out. It would be the other type of bond over here. And R3, instead of coming out, would go into the back. So they don't overlap, they're not superimposable. That's why we'd see that they're optical isomers. And we can see the same thing when we get to octahedral complexes, but they get a little bit harder to see. So making sure we can draw these things, or even better, use your modeling kit to see them, definitely is useful. Oftentimes these things start showing up when we have rings that are attached to our central atom. So here I have a 5-membered ring. Here's another 5-membered ring that includes that transition metal there in the center. But same thing applies. We're going to draw the mirror reflection here. So right now we've got our mirror image. Let's see what happens when we rotate it. As I rotate it by 180 degrees to get those green spheres, those green atoms over into the same position, look what happens. So over here in the original complex, it went back, up, and then comes down. Where now, if we look what goes out the back, it goes down before coming up. Over here on the left-hand side, we would come out, go down, then up, whereas here we'd go out, up, then down. So again, two species that are not superimposable, even though they're mirror images of each other, therefore they are optical isomers. Constitutional isomers are something else that you're probably pretty familiar with from orgo. This is where we have same formula but different connectivity. Good examples here below. The family of C6H12 isomers, like cyclohexane, 1-hexene, 2-hexene. We can look at now making like 3-methyl-1-pentene, etc. There's quite a few in this family here, but there are now so many different ways you can draw these, but it's the same formula. They're just constitutional isomers of each other. Now, one of the things different about transition metal chemistry is that they form bonds in a slightly different way. We're going to say that they form what we call these coordinate complexes, where it's bound in a very different state. So instead of thinking about sharing electron pairs, this is where a species, for example, this NH3, is going to share both of its electron to that central cobalt atom here. So both of the electrons being shared, quote unquote, are coming from what we call the ligand. And we can start making these complexes like over here. We form this hexaamine cobalt complex over here, where we have now these 6 things interacting over here in what we call this coordination compound. We'll talk more about coordination chemistry later on this semester, but just now recognize that it's another way of looking at complex ions. So in this case, we've got a +3 ion that we form because we have nothing on here to balance the charge. So eventually we're going to have some anions in here to help make up for that. And that's going to lead us to some different types of isomers. First one we can think about is that of coordination isomers. So let's take a quick look at these complexes here. You can do the counting here, but I've got the cobalt with now 5 ammonia groups around it, 1 chlorine, and now a counterion of bromine. But we could swap out because we remember chlorine can be chloride and bromine could come on and be linked to the cobalt. That's perfectly allowable. So this would be a coordination isomer. Another type of coordination isomer, here we have this kind of big inorganic complex where our positive ion is this complex of zinc with ammonia, and our anion is over here with copper and chloride. We could just swap which ligands go to which metal. So I could go to the copper with the ammonia ligands, and I could put the zinc with the chloride ligands. We haven't changed the formula, we haven't changed the charges of anything, but we definitely have fundamentally changed the chemistry here. So these are our coordination isomers. Last type that comes in here, the thing that's kind of interesting about these coordination complexes is that they can kind of move around a little bit and they can form in different ways. So for example, this cobalt complex, again, cobalt is a great example, we can bring in an NO2 ligand to bind to the complex. And we'll see that it can either bind through nitrogen or through the oxygen. So it's the same compound, it's just now binding in a slightly different way. Again, they're going to have different properties between them, and that will lead to some kind of interesting things. These are kind of harder to find because you have to have two different things that can link. So the most common examples here we're going to see are compounds that involve NO2 minus, thiocyanate, or the sulfite ion here. So they're pretty easy to spot in that regard. You just kind of have to look for those types of anions. All right, so that's where we are on isomers. Not a whole lot new there, but just kind of now extending it to what we see different in inorganic chemistry. As always, we'll do a little practice on this, make sure we know where we're at. If you have questions, obviously, let me know. But until next time, be excellent to each other.